Hiya and welcome to lesson 2. Today we're going to be talking about fractional distillation, but first retrieval. So like I said in the first video, all of our lessons this week, our retrieval task is going to be a bit on the calculations, which is the last chemistry unit we did. So going back then to moles. So I've given you the equation there, moles is equal to mass divided by mr being the relative formula mass, which is what we did last lesson. So calculate the number of moles in 3 grams, that's our mass of sodium hydroxide. So you must find the relative formula mass first. So pause the video, work it out, and then we're going to move on. Okay, so let's see how you did then. So mass is 3 divided by the relative formula mass of sodium hydroxide, which is 40. So sodium is 23, 16 for oxygen, 1 for hydrogen. So you divide 3 by 40 and you should get 0.075 moles. And remember, other than moles, there's no unit, it's not in grams. So today's lesson, we're going to be looking, like I said, at fractional distillation. And basically, this is an important topic because we find out how we can get all the useful alkanes that we're going to talk about from the gloopy crude oil that's dug out of the ground. So we're going to compare the differences between the alkanes and what we get out of crude oil first, and then we're going to look at how it actually works, and then we're going to look at why it works, because obviously to get those higher marks you need to explain what and why these things can happen. So your first task I want you to do is very easy, spot the difference. You've got propane on the left hand side, you've got fuel oil, which is another alkane, on the right hand side. What I want you to do is I want you to pause the video and I want you to list the differences between these two alkanes. Everything you can think of, using those images to help you. Okay, so let's see how we got on. So if we think about propane first, you can see that it's got a much shorter chain length, okay? And that then will affect the properties of it. So propane, it's in a gas canister because it is a gas. Shorter the chain, the more likely is that you are going to have a gas and not a liquid. So it has a very, very low boiling point, and therefore that's what makes it a gas. So it boils much lower than room temperature. It has a very low melting point, and it is more runny. So it has a low viscosity. Viscosity is a word that you're going to have to be able to use in the correct context. So if something is viscous, it means it's really, really thick and gloopy, like crude oil in the top left-hand corner. If it has low viscosity, it means it's more runny and will flow. So if we look at fuel oil, you can see from the displayed formula, it has a much longer chain length. It does have another name with the ane on the end, but we use it for fuel oil. As you can see, the big tank above the diagram. It's a liquid, so you can see the picture on the right. Fuel oil is a liquid, propane is a gas. The longer the chain, they start moving from gases into liquids, and it's because the boiling point changes. So it has a much higher boiling point than propane would, and therefore it has a higher melting point, and it's much less runny, so it has a high viscosity. So we're going to talk a little bit today about these properties and what makes them more viscous and a higher boiling point, and how that is actually useful to us, because we separate them from crude oil based on these properties. So 2 very, very key points that you'd be worth writing down. The longer the hydrocarbon chain, the higher the melting and boiling point, and it is the boiling point that is really, really useful and crucial for today's lesson and everything really. It's not, you won't talk really about the melting point of hydrocarbons, it is all about the boiling point. That is the really important point. And the longer the carbon chain, the more viscous, so the less runny it is. So it's thicker, it doesn't flow or pour as easily. So two really, really important points that we are going to use, especially the one about the boiling point, throughout today's lesson. So what we're going to do now is we're going to describe how fractional distillation actually works. Now, on class charts, you will have the diagram of the setup. It is worth printing that off or making a copy of it if you can. I'm going to use the diagram, and we're going to ideally annotate it as you go along. It's really important that you can label it and see where the different fractions come and things like that. And we're going to talk through how it works. I've also put a link on class charts to another video that explains it really, really well, so you might want to watch that in addition. So, crude oil. As we've already talked about, we've seen probably on the news that when there's oil spills in the sea from tankers and things, crude oil is black and it's really thick, it's really sticky, and in that form, it is really useless. However, we can split it into all these different things. So liquefied petroleum gas, or LPG, it's what contains propane and butane. That's what you're going to use for your patio heaters, your camping stoves, your gas barbecues. Anytime you've got a canister, that's the kind of thing that you're going to have in there. Petrol and diesel used for cars, obviously, in lorries and trucks and things. Paraffin, again, used to be used in lamps. Heating oil. Heating oil can be used to heat houses that don't have gas central heating. So if you live out in the countryside and you don't have a gas supply, you can use heating oil. And like the picture we saw before when we were looking at fuel oil, it's very, very similar. You have a tank in your garden that you get filled up, and that provides your central heating instead of gas. Fuel oils, very similar, and they go on to be used for fuel for tankers and things like that. And then bitumen, which is the least useful, it's kind of the residue that's left over, can be used for tar. So we can see here lots of different uses for things that come from crude oil. We also, and you're going to learn about this later in the week, use them to make plastics. So everything that you have that's made of a plastic comes from crude oil. So very, very, very useful. But in the state that we dig it out of the ground, it's useless and we can't use it in that form. So we have to use fractional distillation in order to make it useful. So we get from this to this by fractional distillation in an oil refinery. So sometimes you may pass these, and basically they have lots of columns, and you'll see why they have columns very shortly, because it separates things about using their boiling point. So crude oil is separated into fractions by fractional distillation because they have different boiling points because of the different sized hydrocarbons. So we want to be able to separate each of those hydrocarbons out, so the butane and the propane, and the petrol, which has got octane in it, the diesel. All of these things are made of fractions with different number of carbon atoms. And as we know from the start of the lesson, the different number of carbon atoms, the longer the chain, the higher the boiling point, and that is really, really useful to us in this process. So this is your diagram then. Hopefully you have a copy of this from class charts. If not, definitely do make note of the diagram, scribble it down so you can annotate it, or if you can print it off, that's also brilliant, or you could put it into a PowerPoint and annotate it. Because what I'm going to do now is I'm going to talk through how a fractionating column works, and we need to be able to, down the side, annotate these little bits to show the order, because you do need to know the order in which the different fractions are separated. You can get asked that in an exam. It's often a little gap fill where they have some of them filled in and you need to put the names of the other ones. So I'm going to briefly talk you through it. Like I said, there's also a video on class charts that will help you understand this process a little bit more. So this is what we call a fractionating column. Obviously, if we were at an oil refinery, we can't see this. This is all internal and we're just looking at a cross section. Now, at the bottom, you can see on the left, it says heated crude oil. Crude oil, as we know, is a liquid, a very, very viscous liquid. And what we have to do is we have to heat it up and get as much of it as possible to turn into a vapour. Now it's heated to roughly 350 degrees C and it enters the fractionating column. Now most of it is a gas, but not all of it. So you can see at the bottom that, sorry, you've got your temperatures there. You see at the bottom that some of it is tapped off automatically, and that's the residue of the stuff that doesn't vaporize, doesn't evaporate, doesn't turn into a gas at 350 degrees C. That would then go to make the tar for roads. Now we can see it's heated at the bottom, and at the top it's only 25 degrees C. So some of our hydrocarbons, when they are collected off that top tube, are still in a gas. What we do is we collect them as liquids, but sometimes they are a gas, so those ones are collected at the top. Now, you can see from the colours that it's a lot hotter at the bottom and cooler at the top. This is absolutely crucial because as we know, when gases are warmed, warm gases rise. Now, because of the different temperatures in the fractionating column, some of the fractions, as you know, we've got this big mixture of lots of different hydrocarbons. Every hydrocarbon, different length chains, mean that it's got a different boiling point. So when it gets just below its own boiling point and it's too cool to be a gas anymore, it's going to turn into a liquid. And that's what happens at each of these little taps off the side. So the first, the gas goes in and it starts to rise. Now, the column cools very quickly. So anything then that would boil above 300 degrees C would cool, would condense, would turn into a liquid and would be removed at the side. And the rest of the gases continue to rise. It gets a bit cooler, so more fractions cool, condense and are removed from the side. And this continues all the way up the column until you get to the top. It's about 25 degrees C. And the ones that are still a gas are then removed from the side. Now, these are called refinery gases. These are our LPGs that we've just been talking about, butane, propane, and things like that. So they remain a gas. They go and get bottled, and we use them for camping and barbecues and things like that. So the next ones from the top would be the petrol. So we've got our bottled gases, and then we have petrol, which are used for cars. Now, you will need to know this order going down the fractionating column. You also need to know the uses for each of these. So the next one down would be naphtha. This is used as a raw material for making chemicals. Kerosene, which is used in aircraft fuel. Diesel oil, now obviously we use this quite frequently in cars, lorries, buses, things like that. You've got your fuel oil near the bottom, which is used for ships and power stations. And like I already said, the residue down the bottom is something called bitumen, which is used for tar. So it can be used on roads and roofs because it's a good waterproofing agent. So we can see there that we've got lots of different products that have all come out of one mixture of the crude oil. Now, like I said before, each one of these has a different boiling point. So if we look down this arrow down the side, at the top, we're going to get the smaller molecules, the ones with the much lower boiling points. They're very volatile. They flow easily and they ignite more easily. So we use them for burning. All of these are used for fuels, but the ones near the top are the things we might need to actually set on fire. So like camping stoves, like the gas that comes into our house that we would need to ignite. That is why we use the shorter chains, because they ignite more easily. As we go down the column, the chains get longer. So as the chain gets longer, we know they get a higher boiling point, and that's why they collect near the bottom where it is hotter. So they're not very volatile. They don't flow very easily. We said the viscosity increases. So if you were to look at fuel oil, it's a lot thicker and a lot less runny than something like gasoline or naphtha would be. And they don't set on fire as easily. Okay, so like I said, you can also watch the video link that I've put on class charts that will explain this, but I would advise you to pause the video and make some notes on your diagram of this. The key points down the side are very, very, very important. So now you've done that, what I want you to do is I want you to put these stages in order. So the first one's done for you. Now I've just highlighted them in different colours so you can see them a little bit more easily, but I want you to put these different stages in order of how the fractionating column helps us to do fractional distillation. So pause the video and then we'll go through the answers. Okay, so like I said, the first one's already done for you. So the crude oil is heated to about 350 degrees C and is turned into a gas. We know the crude oil is a mixture of hydrocarbons with different boiling points. If it wasn't, then fractional distillation would not work. The point of it is that everything inside it will boil at different temperatures because of the different chain lengths. So the crude oil vapour enters the fractionating column and rises up the column. The column is hotter at the bottom and colder at the top. Again, this wouldn't work if this didn't happen. As the crude oil rises up the column, some of the hydrocarbons will be cooled to below their boiling point where they will cool and condense into a liquid, and this liquid is collected. The process is repeated up the column. The shorter chain hydrocarbons are collected near the top and longer chain hydrocarbons are collected near the bottom. At the very top, very short chain hydrocarbons are collected as gases. So hopefully you did really, really well and you got all 9 of those in the right order. It's just a brief overview of how this works. Obviously making sure that you understand that because the fractionating column is different temperatures, when a hydrocarbon cools enough to just below its boiling point, it will turn back into a liquid and then can be removed. So everything that is removed at the side taps on the fractionating column, it is when they have turned into a liquid because they've gone just below their boiling point. And that's why the chains get gradually shorter as you go further and further up the fractionating column. Okay, so now we're just going to very quickly talk about, we've done already, we're going to look at why this happens, just to make it absolutely explicit, and then look at a couple of questions. So we've got there the order, and we've said, why does this process work? And we've got a little hint that says, what do we know about the chains of different lengths? So basically this works because crude oil has a mixture of hydrocarbons with different lengths of chains, and these different lengths of chains have different boiling points. If they didn't, I've said a couple of times, this would not work. The different boiling points allow the mixture to be separated, and they have different boiling points because of the different lengths in chain. So the longer the chain, the higher the boiling point, that we said right back at the beginning, which is really, really, really important that you understand that and that you can apply this to this scenario. So lastly then, what I want you to do, download your sheet of questions from class charts. Here it is. It's only small, this is just an example. Work through it. There's only about 5 questions on there, just to show your understanding, and we'll go through the answers in a second. Okay, so very, very quickly, first question, this is an example of fractional distillation. Question part 2, each fraction has a different boiling point. This is why it all works. 1B, answer is contains hydrocarbons, has a high boiling point. Those answers are in that order. 1C, which one is pentane? It's the last one, C5H12. Apologies if you can't see this very well. Now, when we're matching up the hydrocarbon, the alkane to its use, petrol is used in cars. diesel is used for buses and lorries. Now, obviously, we know that diesel can also be used in cars, but you don't get buses and lorries that run on petrol. So you just have to kind of think sometimes it's process of elimination. If you're unsure, go back and try it afterwards. There is only one line from each use to each hydrocarbon. Fuel oil is used in heating systems. And lastly, repeated question, you do get this one a lot. Why does this work? Because each fraction has different boiling points. If you've any questions, fire an email over to me or ask me on class charts, but I hope this has been really helpful to you. And the next lesson, we will be looking at how we get other products from crude oil.